So last time we defined the second fundamental form and mean curvature, Gauss curvature, and in a sense everything is based on just generalizing those simple ideas. There's nothing new in the story when you go to higher dimensions except for the complications. But before let's do an example. We did the sphere, so let's do some other simple example. And this is the catenoid. ID. So it's you take a hyperbolic cosine and rotate it around the z-axis, and you get a catenoid. Okay, so if I write it down, the graph would be x, y, and z of x, y, where z is cosine z equals the square root of x squared. Hyperbolic cosine of z equals the square root of x squared plus y squared. And we could try to find the mean curvature, Gauss curvature in terms of x and y, but you can see that that's really not the good variables because it's a problem that's calling for polar coordinates. So if this is the x-axis, y-axis, z-axis that way, it's really silly to work with x's and y's, so it's a good little exercise. So let's let x equal r cosine theta, y equals r sine theta, and z stays equal to itself. So now the catenoid is x squared plus y squared, square root is r, so we have r. So the catenoid is r hyperbolic cosine of z. So the good variables would be to write the catenoid as x, y, z, which is, so x, y, z becomes, x is, if I write x is r cosine theta, right? But r is hyperbolic cosine z. So hyperbolic cosine z cosine theta. Y is r sine theta, but r is hyperbolic cosine z. So hyperbolic cosine z sine theta. And z is z. So that's the catenoid in local coordinates. So now the local coordinates, which before were x and y, and now z and theta. Okay, so that makes the computation comparatively easy. So let's differentiate first with respect to z. So we'll call this the vector x as usual. And now we can compute the second fundamental form for the catenoid. So I have to take partial, the usual stuff. Partial, which one is first? I had the right order. Z, right? So let's do z first. So two derivatives of z. Partial z theta. Partial z theta. And I did not finish because I have to remember to dot it with the normal. So that would give the second fundamental form, but as I said, we also have to divide through by the determinant of the metric. So I have to take the determinant of the metric downstairs. And what's the metric? So anyways, we'll take the determinant of the metric. And this will give the second fundamental form. Okay, so first, what do we need? We need the normal. And at the same time, we need the metric. So that means I have to take, before I can take the second derivative, which makes sense, I have to take the first derivative. So what's the partial of x with respect to, which one am I doing first? Z first, right? So partial of x with respect to z is derivative of the hyperbolic cosine is the hyperbolic sine. Is that right? Cosine, sine, right? Okay, the hyperbolics, I have to always remember. Hyperbolic cosine, let's review, is e to the z plus e to the minus z, and hyperbolic sine is e to the z, or divided by 2, and e to the z minus e to the minus z divided by 2. So when I differentiate the hyperbolic sine, this one switches, and I get hyperbolic sine. Okay, hyperbolic sine, cosine theta. Vice versa, when the next one is again hyperbolic sine, sine theta, and the last one is 1. Okay, now I have to take the partial derivative of x with respect to that with theta. So I got hyperbolic cosine. Derivative of the usual cosine is minus sine theta. Derivative of the usual sine is cosine theta. And the derivative of z with respect to theta is 0. So now we found the first derivatives. So it tells us, first of all, what's the metric. So the metric is sine, first one is sine, this one dotted with itself. So you get sine, hyperbolic sine squared, cosine squared, hyperbolic sine squared, sine squared. So when we dot it with itself, let's see, what did I say? So we had hyperbolic sine, just hyperbolic sine squared. Right? Because cosine squared theta plus sine squared theta equals 1. Now let's do the theta with the theta. And we get hyperbolic cosine squared. As I get cosine squared, sine squared theta plus cosine squared theta. Now I have to do the cross to see what this, if there's any cross. So let's see. So this would be partial of the vector with respect to x, partial of the vector with respect to theta. Let's hope it's 0. Okay, so I get sine, hyperbolic sine, cosine, sine, cosine with a minus sign. The other way I get hyperbolic cosine, sine, cosine with a plus sign, so we're lucky, and the last one gives 0, so we're living very nicely. So we found the metric is G11. It's always nice to do this example. So the G11 was hyperbolic sine squared. And the G12, those one?
Plus 1. dx over dt squared.
Which one?
Sine squared plus 1.
Oh, this was hyperbolic sine squared plus 1, let's see. Because this one was, this one?
Yeah.
Okay, let's see. So it was times, it was hyperbolic sine squared times, you probably,
just the last component, 1.
oh, the last component is, oh, 1. Thank you. So it's hyperbolic sine squared plus 1. 1 times 1 is still 1. A useful fact. Okay, G12 is still 0. And G22 is still cosine, hyperbolic cosine squared z. Okay, so what's the determinant? Well, what's hyperbolic cosine, hyperbolic cosine squared z minus hyperbolic sine squared z is 1 or minus 1? Okay, so 1 plus hyperbolic sine squared is hyperbolic cosine squared. So this is hyperbolic cosine squared. I did it right? 1 plus hyperbolic sine squared. So the determinant, which will go in the denominator, is G11, G12, G12, G22, which is hyperbolic cosine squared, 0, 0, hyperbolic cosine squared. So you get hyperbolic cosine to the 4. Okay, so in the example we now know that this one in the denominator okay, now we have to find the normal. Right here. So I have to take the cross product. Okay, so I have to do, right, in this case, that wouldn't be ijk, but it's still the cross product. Okay, it's, well, it is the component wise. This is in fact, it is the ijk component because we've put it in the Cartesian coordinates. This is still the component in the I direction. So the normal is still exactly ijk. So it's hyperbolic sine z, hyperbolic cosine theta, hyperbolic sine z, sine theta, and 1. And this one is hyperbolic cosine theta, z sine theta, hyperbolic cosine z, cosine theta, and 0. So the only component, let's see, when we do I component, we get hyperbolic, this one gives 0, and this one gives hyperbolic cosine z, cosine theta. J gives this one times that one, minus this one, which is minus hyperbolic cosine. You have to be careful. It's a minus, and this one is also a minus. It's 2 minuses, plus, and now we get another minus, so minus. And last but not least, the k, which is this guy times this guy, was hopefully it's, let's see if it should be 0, let's see. So this is sine, no, sine cosine, maybe it's not 0, let's see, it's sine, hyperbolic sine z, cosine z, this one, and it's cosine squared theta. And this one comes back the other way with a minus is a plus, plus sine squared theta. Okay, so now we know n. Of course, I have to normalize this, make it a unit vector. Okay. Now I take the dot product of the n with these guys, and I pick up the components. Okay, so I won't, it gets a little bit messy, but the n was, has a common factor, this is correct. So the n is normalized, so if you factor out the cosine z, the n is this vector, all with the common factor cosine, hyperbolic cosine z, and then divided by its magnitude. So far, so good? Okay, so let's see what we get. We can pick out the answer, not so bad. Let's see. Can I erase? The picture isn't so crucial. Let's see if we can pick out the components. So if I can pick out the components, I had it here. x11 dotted with n. Let's see. x11 dotted with n. And let's just find the Gauss curvature, because it's, so what's x12 dotted with n? I think that's 0. x12 is take the partial with respect to z, which we did. Then if I take the partial with respect to theta, I get minus sine theta. Let me just do this one. So I get minus sine theta. And this one becomes cosine theta. This one becomes 0. Now let's look at that dotted with n. So when I dot it with n, I'll get a sine, hyperbolic sine z sine theta, cosine theta. And this one will give me a hyperbolic sine z cosine theta minus sine theta. They cancel. Okay. So immediately we see that these terms are 0. So now all I have to do is take the product of those two guys. First I have to take the dot product and with n, and then multiply. Okay. Now this one I think is, it should turn out to be, let's find out this one. I think one is 1 and one is minus 1. Let's just see. Okay, so I have to do z with z. You'll believe me if I can do, let's do, this was cosine. Well, let's do, this was partial of x with respect to, let's do this one, because I didn't mess up this one yet. So let's take the second derivative here and compute. So that would be computing this component. Okay. So if I take the second derivative, I get sine theta becomes cosine theta. Cosine theta becomes minus sine theta. Okay, and now let's take the dot product with n. Okay, when I take the dot product with n, I get cosine squared theta right times minus hyperbolic cosine of z. And remember, there was a hyperbolic cosine of z that would have been factored out. Now I have to take minus hyperbolic cosine again, which is hitting the minus hyperbolic cosine. And now I get sine theta. Let me see, it's minus sine theta there, and minus sine theta there is plus sine squared. Correct? So it's minus hyperbolic cosine squared theta times sine squared plus cosine squared. Okay, this is very nice. So it's minus hyperbolic cosine squared z. Okay, so this one you get minus hyperbolic cosine squared z over here. Okay. Well, I got somehow, let me see, cosine fourth. Okay, I'm not, it looks okay. So minus hyperbolic cosine squared z there. I think here you get the reverse sign. Plus hyperbolic cosine squared z. If I did that. But I didn't divide through by the normal. Okay, so if I multiply this guy times this guy, I get the minus hyperbolic cosine fourth. Cancels the hyperbolic cosine fourth. So all that's left for the Gauss curvature is 1 over the minus 1 over the normal, magnitude of the normal. Okay, so the Gauss curvature is minus 1 over the magnitude of the normal, and the magnitude of the normal is also cosine fourth z. So what do we learn? First of all, the Gauss curvature was negative. As opposed to the sphere, which was positive. So because it's looking this way as opposed to looking that way, the Gauss curvature changed signs. Okay? And we could even find the principal curvatures, which would be just each one, the product, of course, the principal curvatures. So each one, the principal curvature, is the same. So the principal curvatures are equal, and their product is minus 1 over hyperbolic cosine of 4. Or 1 is plus and 1 is minus. Their product, their reverse signs. Okay, so that's somehow one of the nicest examples. So the Gauss curvature is negative, and why does it work? So there's something deep here. Okay. It's not clear that you can always build a surface with negative Gauss curvature that goes on, that can be locally okay, but that globally defined surface as the catenoid goes on forever. Why does it work? Okay, and it's a deep result. It's because the Gauss curvature, while it's negative, as z gets very big, e to the z gets very big, e to the minus z is negligible going upstairs, or vice versa. If we go minus z going to minus infinity, this guy gets very big and this guy gets negligible. Either way, the Gauss curvature goes in magnitude, goes to 0 as magnitude of z goes to infinity. So we're trying to put a surface of negative Gauss curvature in R3, and can we do it globally? And the answer is yes. I just gave you an example, but it tells you what the underlying result. If you wanted to prove a theorem, when can you put a surface of negative Gauss curvature in three-dimensional space? This one works because the Gauss curvature, while it's negative, goes to 0 fast. So it's looking flatter and flatter. So it's good to have flatness at infinity. No surprise that when people prove local existence theorems for the Einstein equations, what do they want? They want flat space at infinity. It's the best boundary conditions. Now here it's how fast does it go to infinity? Here exponential is very good. You don't need exponential. Some algebraic decay. And that's, people have done that. Finding the S.T. Yao from Harvard proposed the question, what's the sufficient condition, algebraic decay, that will get you a surface in 3 dimensions? So even starting with a simple example motivates interesting problem. And it's actually a problem in system of hyperbolic conservation laws. Method of characteristics works. Okay, let's do the Gauss theorem. So there was my example to start the day and to motivate problems in PDE. Okay, so this is famous Gauss's theorem egregium. So I don't know what the Korean translation, I don't know if egregium is, but the English translation is somehow surprising, for lack of a better. So Gauss was very happy, and since he wrote in Latin in those days, about 1830, because that was the language everybody could understand each other, so he wrote Theorem egregium. It was a surprising result. So let's state it, because all of the story is based on the Gauss theorem and its generalizations. So the Gauss curvature, the theorem is the Gauss curvature. Oh, my handwriting isn't so. Curvature is intrinsic. I'll write it out in words. Specifically, there is a local coordinate system call it here it's called U1, U2, about any point P in a C2 surface in R3, so that the first fundamental form form G, or a Gij, at P is the identity. To first order. And in these local coordinates, it's longer to write than to prove. The proof is one line after you make all this stuff, but it's so fundamental. U2. Okay. So it says, it says that there's some local coordinate system, okay, that you can always find the Gauss curvature just in terms of the metric. Okay, that means if you know the first fundamental form, you don't know the second fundamental form, that's higher derivative, so it sounds, can't get something for nothing. But it says if you know the first fundamental form, the metric, okay, you may not know the second fundamental form, okay, but you know its determinant. So the determinant is an invariant. Okay, and the proof is, let's just think of the computation. Okay. go back, because we already did it. So let's go back to the x, y, f. So you give me a surface, and I can always choose the tangent, pick a point, choose a tangent plane to the point. So now the tangent plane is just the xy horizontal plane. So we made things simple. So that's z equals f of xy. So that's how we set up the local coordinates. Okay? And f of x equals 0 and f of y equals. So f of x at the origin, we moved everything to the origin, and the first derivatives are 0. Okay. So what was the metric in that case? We know the metric. We did it before. What was G11? It was, we had to take the first derivative, so the metric was 1 plus f sub x squared. That's how we found the metric on the surface for all points. Okay? And we had G12. What was G12? It was f sub x, f sub y. And G22 was 1 plus f sub y squared. If I did that correctly? Okay. So in particular, at this point, G11 is 1, G12 is 0, G22 is 1. So it looks like the identity at that point, exactly as the theorem tells us to do. So I found some way to make it look like the identity. Okay. Now what was the Gauss curvature? Well, first we have to find the second fundamental form. Well, it's 1 divided by the, let's find the second fundamental form at the origin. What's the second fundamental form at this point? Because that's all we're going to do is find the Gauss curvature at that point. So it's 1 divided by the determinant of g, but the determinant of g is 1. Okay. And here was, take the second derivative of f and dot it with the normal. What's the second derivative of f? Well, the normal, take the second derivative of the Hessian, x, y, f of x, y. Second derivative is 0, 0, and then f sub x, x. Dot it with the normal, which is 1, 0, 0. 0, 0, 0, 1. So it's only f sub x, x. Here, f sub x, y. Here, f sub x, y, which is how we started the lectures anyways. So no surprise. So what does it say? Let's say what the theorem, it says the Gauss curvature, if this is true, it says the Gauss curvature is, let's see, it says take this, oh, what is the Gauss curvature for this one? Okay, it's the determinant, so it's f sub x, x, so let's find the Gauss curvature. So it's, can I use subscript? It's a little ragged. So it's f sub x, x, f sub y, y, minus f sub x, y squared, and if the determinant of the metric wasn't equal to 1, then I'd have to divide through. Okay, but it's 1. Okay, what is the derivative of G11? Now let's check this with u1 equals x and u2 equals y. So what's the derivative of G11? It's differential with respect to x, right, gives 2f sub x, let's say 2 partial of f with respect to x, right, partial of f sub x, x. Sorry, is that okay? Then I have to differentiate with respect to y. So this will give a y here, right? And then this guy differentiated with respect to y, this guy stays the same. Okay, so that's the first one, and then it's 2 partial of f with respect to x, and this guy was, if I'm not mistaken, was for x squared partial y. Did I do that right? Okay, but when x equals 0, y equals 0, this guy is 0. So the only one I have to worry about is that one. So it's partial of partial g with respect 1, 1. I differentiated 2 times the partial of f sub x, f sub y. Let's hope I get the right answer. Okay, because I've done it here. Here I get x, x, y, y. So let's see. So how come I have g11 partial g11? So this should have been g12. Now I see why. Okay. So let's go back and do it correctly. Okay, so not perfect. Try again. Okay, so now let's do partial of g12. g12 with respect to x is partial of f with respect to x, partial of f with respect to y, partial of f with respect to x, partial of f with respect to y with respect to x. That's g12 with respect to x. I have to do g12 with respect to y. Let's see if we can do it in the head. So when I differentiate with respect to y, when I differentiate this guy with respect to y, I'll do it slowly. I'm going to differentiate with respect to y. When I differentiate this guy with respect to y, I'll get this derivative with respect to y times this guy, but that'll give 0. Plus this derivative with respect to y, and I get that one. I differentiate this guy with respect to y, I get something. In fact, this guy repeated, plus this guy with respect to y, but then multiply times 0. So when I differentiated g1 with respect to y, I got f sub x y squared, okay, plus f sub x times f sub y. And then I'm supposed to take that one and subtract off. Now I have to take g22 with respect to y. So here's g2, 2. I differentiate g22 with respect to y once. I get 2 f sub y, f sub y, f sub y. So that's the first derivative. Now I differentiate one more time. Of course, when I get 3 derivatives, this is multiplying 0, so all that survives is this guy f sub y squared. Okay, so I have, f sub y squared. F sub y, f sub y. So I get 1/2 f sub y, 2 times f sub y squared. Okay, the other one will give me 2 times f sub x squared. So let's see, what do I have here? So do I have the determinant? So it's it looks, did I make a mistake? Should have an f sub x, x, y, something.
You're supposed to take it x for g22.
Which one is the?
So So in the formula,
Yeah.
G22.
2 is supposed to be with respect to x. Okay, I'll keep trying. Thank you. So we got to this one right. So 2 with respect to x. Sorry. So 2 with respect to x. So it's 2 f sub y x. Then I have to do again with respect to x. So I get f sub y x squared plus 0. Thanks. So let's see. So it's f sub x y squared with a 2. But that the same thing with respect when I do the that was G22 with respect to x. Now I have to do G11 with respect to y. But it looks exactly the same. Now it's looking good. Okay. So now we write this as k. So I have f sub xx, f sub yy. The 2's cancel. So one of these cancels one of those, and I'm left with minus f sub xy squared. Which is precisely the determinant. Okay, after. So what did we prove? We proved Gauss's theorem egregium, which says that the Gauss curvature only really depends on the metric. So the Gauss curvature is intrinsic, okay, which is a great result, and everything is based on that idea. So let's do an example. An experiment. We'll do the experiment. My favorite experiment. So I don't. It's an experiment, and we can all do it. Okay, so I'm going to take a piece of paper. Okay, we know how to find the distance on a piece of paper. All right. So if this is the local coordinate system? Okay, so this would be u1, u2, and if I want to know the s squared is the u1 squared plus the u2 squared. Pythagoras' theorem. Okay, so we know distance on a piece of paper, and that's very nice. Okay. So if I take the piece of paper, what's its Gauss curvature? Well, it's flat. So the Gauss curvature is 0. All the second derivatives are 0. So the Gauss curvature is 0 for the flat. Now let's deform the paper. Okay. So now it has some shape. So like that. So now z equals f of x, y or u1, u2. So this was u1, this was u2, and z is a function of u1. So u1, u2 is still u1, u2, piece of paper. Okay, what's the metric? Well, it's something, right? There's some new metric. So it's 1 plus f of x squared, 2f of xy, let's use x, the x squared, the x dy, 1 plus f of y squared, dy squared. Okay, so I deformed it, okay, but the distance between 2 points on the paper, measuring along the paper, not, so if I want to know the distance between this point and this point, not this way, that's not allowed. It means you're Columbus, you have to go all the way around, you can only be on the surface of the earth. So if I want to know the distance between here and Madison, Wisconsin, I I can't cut through the Earth. Not allowed. You need a very good tunnel. No tunnel between here and the United States. Too bad, but no tunnel. So you have to go on the plane. So, but imagine you're going on a ship, then you have to go on the surface of the Earth. So, but the distance, okay, since it's paper, it's not elastic, it didn't deform, so the distance is the same. Okay. That means whatever the F is, that the metric had to have been the same. Okay. Okay. But the Gauss curvature only depends on the metric. Remember, we just proved that. We just wrote down the formula. K is some derivative of G. What was it? 1, 2. And it was U1. It was 1, 2 here. I erased it. So the Gauss curvature only depends on the metric. That means if the metric doesn't change, the Gauss curvature doesn't change. So if the metric doesn't change, the F will change, but not the metric. If the metric doesn't change, then the Gauss curvature doesn't change. Okay. The language people say is that this is an isometry. Distances didn't change. So under an isometry, the distance, I make a point here, I make a point there. I measure the distance. I turn the paper, distance didn't change. It's an isometry. That means the Gauss curvature did not change. So what's the Gauss curvature for the paper this way? Has to be 0. So let's do the experiment and then, okay, so let's do this cylinder. Okay? If I can do it. Of course I'll ruin my notes, but, okay, so here's the cylinder. I'll draw the cylinder on the board. So I took the paper and I folded it over. So now we have a cylinder. Well, it's not hard to see. What's the principal curvatures? What's the biggest one? There's two. What's the biggest and the smallest? Well, the smallest is going this way, flat. Okay, so one curvature clearly 0. What's the other one? It's the curvature of a circle. So if the cylinder has radius r, the other one is 1 over r. So what's the mean curvature? So the mean curvature here, which is we used capital H. Well, the mean curvature for the paper, flat, 0. Mean curvature for the cylinder, if we don't either divide by 2 or the dividing by 2 is not going to win you a Nobel Prize, so we don't worry about the dividing by 2. Okay, so the mean curvature is 1 over r. But what's the Gauss curvature? The Gauss curvature is 0 times 0. But the theory tells us that the Gauss curvature here better be 0 times 0 as well. And sure enough, it's 1 over r times 0, not a deep computation. So the Gauss curvature, kappa 1 times kappa 2, was 0. So that sets up, since supposedly advertising PDEs, let's finish up with asking the question. So I'll erase and then we'll finish up asking the question. That I mentioned before, but now it can make sense. So what's the PDE question? Since that's the motivation for all the lectures. So what's the PDE question? The PDE question is, you give me a metric, how to measure distances, is there always a surface? So you give me a metric. me a metric. Let's just do it in 2D. So you give me G11, G12, and G22. For example, you gave me the metric here. Is there always a surface that satisfies that metric? Well, the easy one was, of course, the flat piece of paper satisfies when the metric is G11 equals 1, G22 equals 1, G12 equals 0, and I get the flat piece of paper. So we solved the problem. Okay, that's the easy case. Okay, an easy one. You knew the answer. So that one works. Of course, okay, the cylinder would have worked too. So if you want to know the difference between a piece of paper on a cylinder, piece of paper flat, and the cylinder, then you have to make a boundary value problem. You want the surface that satisfies some additional properties. But now let's write, what would it be in general? It says, what in applied math we would call an inverse problem. Okay. It's not, as I always say, in undergraduate courses we teach the students, given the line, find how to compute arc length. Or given the surface, how to compute distance along the surface. But this is the inverse problem. It's given the distance, find the surface. So that means we're given, I want you to find the surface, whatever it is. Might look like z equals f of xy. Given the metric, find the surface. But we just have done, I reminded you, that the metric for the surface is, let's write out the x's and y's. That's the G11. That's the G12. And that's the G22. So it's given the right-hand side, that's given, the given stuff, and it actually makes sense, at least in English, the letters agree. G for given, F for find. Given the G, find the F. Maybe in Korean it doesn't sound so nice, but in English it happens by luck to work out. Given the G's, find the F's. Okay, now you think about it, and you're all experts in PDE, and you look at it and you say, oh, what did we learn about PDE? Oh yeah, elliptic, hyperbolic, parabolic, second order equations, method of characteristics, and you look at it and say, that doesn't look like the kind we had in the course. Okay. First of all, it's the highest derivatives squared. Okay. Okay. So not so easy. Here it's cross product of higher derivatives. Okay. Here, again, higher derivatives squared. So finding the metric, not so easy. So that's one thing. So it would be called a fully nonlinear problem. Then you think about it, okay, let's see if we can use a trick. What's one trick? Well, we remember that given the metric, now we know the Gauss curvature. So that changes it to a problem in second derivatives, because the Gauss curvature, which we just computed, was the determinant, because the normal is, we'll just look for the normal being 0, 0, 1. So you want to solve this one, okay, divided by its square root of 1 plus f of x squared. So Gauss curvature times it's the metric, so it was 1 plus f of x, whatever, all the whole metric stuff. So you have to take the determinant of the metric. So it's this guy times this guy minus that guy squared. So the determinant of the metric. Okay, well, you know the metric, so you know the determinant of G. You know K from Gauss's theorem egregium. So you have a formula for K in terms of G. So it says, given the right-hand side, again, find the F that works. But this is a determinant problem. And you go hyperbolic, elliptic, parabolic, method of characteristics, none of the above. Again, fully nonlinear. In fact, it's mon Jean-Pierre. Yeah, fully nonlinear. So it's no surprise that the inverse problem has always been a challenge. On the other hand, why did people worry about the inverse problem? And the answer is because originally Riemann wrote down his theory of Riemannian geometry as an abstraction, that there's a G and there may not be an honest-to-goodness surface that we're talking about. Is there a difference between Riemann's abstract theory of Riemannian geometry and the theory of surfaces, maybe higher dimensional surfaces? And that was the question. Is it the same thing or different thing? And that stayed an open problem, and then people did local results, little pieces, but globally, is it a global story? And the answer was not decided until the 1950s, 1950-something. And that was John Nash proved, yes, it's always a global surface, but it might be in very big dimensions. So here the surface is, you give me a metric in whatever, lying over here, but the surface might be much bigger dimensions. So Nash's result, yes, is yes, there's an always surface, but it may be in lots of very big dimensional space. Okay, so that was Nash, and if you want to see about Nash, you can watch the movie. And in the beginning of the movie, so you can get the DVD. Okay, didn't win the Nobel. Nash won the Nobel Prize. The movie won an Academy Award. So everybody won something. I won nothing. Okay, but you can see Russell Crowe plays John Nash, and in the beginning of the movie, one of the first scenes, they show Crowe, that is playing John Nash, because they made the movie through a piece of glass. So you could see him filling the board with long PDEs. And what was he doing? Of course, there was a mathematician who was the consultant for the movie. And he was proving the isometric embedding problem. And it's ironic that Nash won a Nobel Prize in economics, but the math was much harder here than for the economics, but that's no Nobel Prize in economics, so Nash didn't win that. Didn't win a Fields Medal because he had emotional problems, and no prize for that. So that's life. But anyways, this motivates a lot of mathematics to this day. It's 11 o'clock, so a good time to stop. So I'll continue tomorrow, Wednesday's holiday, and then Thursday. Okay. No.